here's our objective, all right? And here are AP topics. When you put something in a solution and stir it up, all right? Big question. If it doesn't, there you go. You made a heterogeneous mixture. Just got two things mixed that you can tell them apart. If you did, you've made a solution. And a solution is most common in chemistry going to be a liquid solution. You can actually have it between any two phases. But this video is mainly about what these things look like on a particle level and why they do and why things dissolve and how to predict whether or not something will dissolve. All right, here's a good definition for a solution. All right, classic example, salt water. All right, now I want to talk about a nonpolar solvent, and that nonpolar solvent being hexane. And I want to talk, here's a molecule of hexane, and hexane, because hexane's electrons are randomly moving around it, there's going to be some areas of high density and low density, all right? And these areas of high density are constantly going to be moving around, all right? Because the electrons are constantly moving around, all right? So these areas of electron density shift in an electron in a, all right, kind of looks like this. It's not, they're not stagnant, but you can draw it as stagnant. This gray area in the back represents the electron crowd. I guess it is kind of like a crowd. And you're just going to have regions of various density where some is going to be negative and some is going to be positive. Or not partially positive. It's like just, it's an area where you have electrons and you don't have electrons. It's not really partially positive. All right? Now, so let's look at what a covalent solvent and a covalent solute look like. This is hexane in wax. Now here's the thing, and here's the hexane. It's just this clear liquid. Now, this is, I stirred it up quite a bit. You can see this is the water, all right? And pay attention to what happens to the salt, the wax at this point, all right? You can see the wax is totally moving around in the solvent. And this is in the water, all right? It's not moving around too much in the water. You can, but in the hexane, you definitely have a lot more interaction because they're moving with each other. And I had just stirred that water up. Now I've got two things of hexane here, and I'm going to reenact kind of what happens before I show it visually. You have your hexane, and it's got its random areas of electron density. And these hexane molecules are going to interact with the paraffin. Paraffin is actually a carbon chain. It's really big and long, all right? And as it approaches the paraffin, what's going to happen is you're going to get the paraffin also has London dispersion forces. All molecules do. But what's going to happen is they're going to be able to kind of interact and form London dispersion forces. All right? And the same thing will happen over here. You're going to have London dispersion forces. And this allows the molecules to move and will kind of encourage them to move with each other. Now, these densities, once again, they're moving around. But the bigger your molecules, the more polarizable it can be, and the more it can interact with your solvent. All right. So here comes the hexane. Here's the paraffin. All right. It interacts with it, and you get something that looks in the end like this. And this is the visual I want you to have down, where you've got these London dispersion forces picking are generating because of you've got these random electron movements making them happen. All right. Once again, the bigger the molecules, the more the electron cloud can be polarized. All right. Just have more electrons moving around. All right. Now let's look at salt and water. All right. This is polar solvent, ionic or polar solute. All right. Now this is water and salt. I'd already added some salt at this point to the water. This is hexane up here. All right. You can see it. There's a little bit of salt there. All right. And I want to watch all of this video. It's 20 seconds long. Okay. Stirred it up. There, it's gone. All right. No. Now, this is hexane in salt. This is the top one. So this is a nonpolar solvent with an ionic compound. And there, it's stirring up. You can see this, it is not going in. All right. It's not dissolving. There's not as much interaction. All right. Now, I want to give you like a molecular particular level vision of this. Here we've got our salt, all right? It's like a crystal lattice. Got two different shapes, white, green, white. And what's happening? So as the salt gets interacted by the water, water is polar. So one end's negative, the oxygen, and one end's positive, the hydrogen, all right? And it comes into contact with the lattice and basically pulls away these various pieces of the puzzle. It takes part of the, gets pulled away, and you end up having several molecules. It's going to go like this. Of water around this would be the cation, because the water, this end of water is positive, therefore they surround the positive part of the salt, all right? And the opposite is true of the anion. The anion gets solvated by the negative portion of water. And what this is going to look like, and the visual I want you to have, looks like this. Here I've got that positive cation with the negative ends of the water, the oxygen, and there's the opposite. Now these dots mean it's not a true bond, it's like fluid, all right? There'd even be more molecules coming out of the page and in back to the page, all right? Here's what we just saw above in text. So in general, things with similar intermolecular forces tend to be soluble in each other. Please don't justify with it like dissolves like. That's not, you're correct, but you're going to need to talk about what's happening in terms of the intermolecular forces. All right? I hope this has been helpful, and have a good night.